I'm so glad that dark is available in OneNote now, or whatever the heck that was. All right.
Oh, turn it on. It's on the other side. Open up the other door on the other side. You can turn it on. Just turn it on low because it's really loud on high. You just spin it to the right. There you go. It was really loud in my last class, and it was plenty cool. I turned it off. It is getting warmer. I agree. Part of the reason is people always open the shades so the sun blinds in. But we also have the issues of it's a south-facing room. It's a brick building. As the sun hits it, it heats up like a brick oven. Which we get to record for posterity because, of course, I'm already recording. So.
Yay! It's YouTube.
All right. Any questions at all before we keep going with things?
You guys.
Am I going to give you homework?
Yeah, wait.
I don't know. Sometime soon.
Because he's gonna ask at some point. What?
I might give you homework problems. It's possible. All right. Well, we started off with talking about different properties of probability. The big ones that we talked about were, of course, if you do the probability of a union, I can break that up as a sum, provided what was true. What had to be true about A and B if I was able to break it up? Yeah. And it'd be mutually exclusive, right? That they don't have anything in common. One of the things that we'll talk about here in a few minutes is what happens if they're not mutually exclusive. What happens if that intersection does contain some possibilities? This was part of our definition for being a probability function. To have this property where you can break it up over mutually exclusive events. The other big thing that we talked about was that the probability of a complement is 1 minus the probability of the event. So those were two of the bigger properties that we proved last time, as well as showing that the probability of the empty set happening was 0. We did that at the end of class. So these are probably the two big formulas that we've had so far. So we're going to get at least one more with the more general union formula, and then we'll build up from there because we'll have ways to figure out probabilities of intersections through formulas and so on. So kind of just building things up from the ground up. All right, one of the next theorems talks about what happens if we have probabilities for subsets. So as a theorem, if A is a subset of B, then what do you think the relationship is going to be between the probability of A happening and the probability of B happening? Yeah, it probably needs to be at least as big, right? So if the event A is contained inside of the event B, then the probability that A happens can't be any bigger than the probability that B happens, right? So it probably needs to be this way. And notice again, one of the reasons why we use this as our subset symbol is it makes us think less than or equal to. One of the reasons why we use that formulation of the symbol. But again, this makes sense, right? Because think about it in terms of rolling a die. The probability that you roll an even number will be a half. The probability you actually roll a 2 is a sixth. Being a 2 is a subset, a sub-event, if you will, of rolling an even number. Right? Same concept. Okay, well, let's see if we can prove this, because the idea behind the proof uses some set theory ideas that we're going to use to do some other proofs. So, one of the more common ways to write sets is to break it up into individual pieces. So let's think about the Venn diagram and see what I mean by this. So if I draw a Venn diagram, and I know that we've got A being a subset of V, I'm not going to draw it that way in this particular case. Let me draw it like this. This is a general diagram. This is not the diagram that we would have for A being a subset of B, right? If I drew the Venn diagram for A being a subset of B, what would it look like? Yeah, A would be entirely inside of B, right? I have the circle for A and the circle for B around it, right? So this is not a Venn diagram for that, right? But one of the things that I wanted to use, and all we have so far are the properties of being a probability function and the things that we proved before, right? One of the properties of being a probability function is a thing that I wrote at the very first thing on this. I was going to say slide, but this isn't a slide because I'm going to scroll it. So, what is the very first thing I wrote on this screen, right? Is that if they're mutually exclusive, I can break it up as a sum. So, if I just look at the set B, if I just look at the circle of B, B is made up of two mutually exclusive parts. Right? B is made up of a part that's inside of A and a part that's not inside of A, right? You agree with that? So in general, we could write B as a mutually exclusive union of the part of B that has a piece with A, right? Union along with the part of B that's not in A. This is just general, right? Has nothing to do with A being a subset of B, right? If I just think of A and B having whatever relationship they have amongst each other, there's a part of B that's in A and a part of B that's not in A. Now, of course, depending on the situation, it's possible that one of them are empty or one of them is bigger. In general, that's what it looks like, right? Everybody agree with that statement? And again, we get the added benefit that that has no intersection. Those are two mutually exclusive events, or sets. And if I think about it in language of probability, it's two mutually exclusive events because A and A complement have nothing in common. Right? Since A and A complement have nothing in common, certainly these sets that are smaller can't have anything that are in common because we're doing intersections. Do you agree with that? You okay with that? It's okay not to be okay, we just need to tell me. Or throw something at me. One of the two. Yeah?
So why can we use A complement in this part? I guess I just don't understand that part.
As far as why am I using A complement?
Yeah.
I'm not even worried about this particular theorem right now. I'm just trying to make a general statement about this set B and how I can write it.
Okay.
So this is my A. A complement would be everything outside of the circle.
Okay.
So that's representing, for this second part, that would be representing, shaded on here, that's representing this part here.
That's A complement.
This is the part of A complement that's in B.
Okay.
Because A complement otherwise would be all this out there too.
Yeah.
Yep. Okay. All right, so now let's put this in the context of the problem. We're given that A is a subset of B. What simplifies? There's a piece of that simplifies. If A is a subset of B, I can write a piece of that thing that I just wrote B as something a little bit smaller as far as the writing goes. Which part of that simplifies? What's there?
The B union with A. Which would be intersect with A.
To be intersected with A, what does it have to be? A. It has to be A, doesn't it? If A is a subset of B, let's think about what the picture looks like. If A is a subset of B, you told me before that the circle for A ends up inside the circle for B, right? We agree? So what would be the intersection of those two sets? What's in both sets at the same time? Everything that's in A. Right? So if A is a subset of B, then this B intersect A part here just becomes A. Oops. Still, I have mutually exclusive sets. In general, we said that A intersect B and A complement intersect B are mutually exclusive, right? So this is still mutually exclusive, correct? I've got a union of two mutually exclusive sets. So now if we do the probability of B, that will be the same thing as the probability of A union B intersect A complement. Right? What can I do? Well, you told me that A and B intersect A complement are mutually exclusive. So what can I do with the probability function with respect to this union symbol? Separate it and make it A? Yep, good. Right? So far so good? Okay. Now let's go back to see what we're trying to prove. Never lose sight of what you're trying to prove, by the way. It helps you for where you're trying to go with the proof. Here's what we're trying to prove. The probability of A is less than or equal to the probability of B. Let's look at our equation. Do I see those two pieces? Do I see probability of A and probability of B? I do, right? Here's probability of A. Probability of B is on the other side of the equation, right? Well, which one? Given the equation, and I'll just for emphasis, I'll write probability of B down here again. Which one has to be the bigger one? Or which one can't be any smaller? Yeah, the probability of B, right? Why?
That's the probability of B union or intersect B complement. You add A equal B.
Good.
And it can't be negative.
Good, that's exactly right. This part here, the probability of B intersect A complement, is being added to the probability of A, right? Can that be negative? Can probabilities be negative? No. Probabilities have to be 0 or positive, right? They're always non-negative. So I'm taking a probability of A and adding something that can't be negative. So the only choice we have is B, probability for B gets bigger, it can't get smaller, right? So since probability of B intersect A is greater than or equal to 0, we must have that the probability of B is at least as big as the probability of A. And that was our proof, because that was what we were trying to get to. And you'll notice in your book, when it gets done with a proof, it puts a little box that's its symbol for being done with the proof. You may have seen that before or not. I don't typically write, I'm done with the proof, because we're done. I go on to the next thing. Okay. But in your textbook, if you see the end of a proof, it'll put a little open box like that. Some books write QED. It's Latin for it's the Latin abbreviation. The abbreviation for the Latin of this has been demonstrated. Some people really think they're funny and will write W to the fifth. W to the fifth is which was what we wanted. I told you they think they're funny. Okay. I typically just stop, but if you see it in the textbook, that's what it means. It just means the proof is over. All right. We okay with that one? Yeah, Maureen.
So how do we know that A, the union of A and the B intersect A complement, how do we know those were mutually exclusive?
Okay, so it goes back up to here for the same reason those were. A and A complement can't have an A complement, because you can't be in A and not in A at the same time. And this is smaller. Because this is definitely inside, anything that's in here is inside the complement. And if you're in the complement, you can't be inside. That's how they have those two. It was for the same reason up here. It's because A and A complement, you can't have anything in it at the same time. And so then when we have the intersection, it's very probably small. Well, not necessarily probably small, but it can't be bigger. You can't. You don't add things when you do an intersection. You possibly subtract things. Right. So that's why. Yeah.
So then what is the B intersect A complement look like on the picture?
On the picture?
Where is it?
It's this part here.
What's on
This one, it would be the outside of it would be the donut.
So it's still inside the A but not, or inside the B but not.
Correct, yeah.
Inside the donut.
Yeah, it's the donut, but not the whole. Yeah.
So, sorry, so just by saying B intersect A complement is saying everything that's within B is not.
Correct. Yeah. So it's in the top picture here. It was this part. And in this picture, it's the donut. Now I'm hungry.
I'll bring in food next time. Go order pizza.
Yeah, pizza, that's true. All right. From this, they get the Dex theorem, which I'll actually refer to as a corollary. And one of the reasons why I'll use that word is corollary is just another fancy word for theorem. It just means it follows directly from a previous theorem. So corollaries follow directly from previous theorems. There's also another fancy name for a theorem, which is called a lemma. Lemmas are used to help prove bigger theorems. So just as vocabulary lesson for the day that you may or may not have wanted. All right. So for the corollary, it says for any event E, or for any event A, the probability of A has to be less than or equal to 1. Which, again, from an intuitive standpoint, this has to make sense. Because, again, if we think of a probability of 1 being a 100% chance that it happens, all this is saying is that an event cannot have a greater than 100% chance of happening. Okay. So from an intuitive standpoint, that's what this says. Okay. But from a proof standpoint, that's intuitive sense of things is not a proof. Where does the proof come from? Well, I referred to this as a corollary. Corollaries follow directly from previous theorems. Well, I just got done talking about this theorem, right? So it must follow directly from this. All right, so let's look at this theorem. It says if A is a subset of B, then probability of A is less than or equal to probability of B. For any event that you have, what do you know it's always a subset of? The sample space, right? No matter what, it's always a subset of the sample space. So we know that A is a subset of S, where S is the sample space. No matter what, any event that you have, it has to be a subset of the sample space. So by the previous theorem, we now know what? What was the conclusion of the previous theorem? Right, yeah, it's sitting right there, right? Probably the bigger set has a greater probability than the smaller set, right? So in this case, with A's and S's, what statement can we make? Good. The probability of A is less than or equal to the probability of the sample space. You said it the same way, just reversed. Yep. Right? That's literally what the last theorem told us, isn't it? What do we know the probability of S is? No matter what. 1. Right? That was one of our properties of being a probability function, correct? That the probability of the sample space is 1. So since the probability of S is 1, oops, we have the probability of A has to be less than or equal to 1. And again, this is why we call this a corollary. It's literally just in this case, just a special case of the previous theorem, right? All we've done is take out the set B and plug in the sample space. Okay with that? All right. Well, one more theorem, and then I'll do problems. Okay. Let's do one more. All right. This is a theorem about how you break up unions. Oops. So for any events A and B, we have the probability of A union B has to be the probability of A plus the probability of B, and then we have to subtract something off. This would be the probability of A intersection B. Before we go through the proof, and the proof's going to be basically like the last proof that we, not the corollary, but the proof of the last theorem, where we write the sets in specific ways to be able to use our formulas for being able to break apart the probabilities for mutually exclusive events. Let's think about why it's true just from a set theory idea. Let's think about it from a counting idea. If I take A and union B, and I want to count up how many things are in the union, one way to do that is just, okay, I'm going to take everything that's in A, and then I'm going to take everything that's in B. Okay? So I count everything in A, count everything in B, and add it together. Okay? That's what the first part would be. But think about what we've done. If I count everything in A, and then turn around and count everything in B, I've counted some stuff twice, potentially. It's the things that are both A and B at the same time. So to get a correct count, I need to subtract off whatever's in both. So think about it this way. If I go out to the parking lot and I count everything that's a car, and then I have to count everything that's red, I counted red cars twice. Right? So I'd have to subtract off the number of red cars to get a total. Same idea here. It's just stated as probability rather than number of things in a set. So if you've seen discrete math, you've seen cardinality of A union B is cardinality of A plus cardinality of B minus the cardinality of the intersection. Cardinality is a fancy set word for number of things in the set. If you are in discrete, you will, that sounded like a weird word. If you are in discrete math this semester, as opposed to being indiscreet. If you're in discrete math this semester, you'll see that. All right, so let's talk about how this proof goes. But it's the same concept as what we did before. So if I do the same ideas here, we would have, if I look at A union B, that A union B can be written as the following union. Think about why it's true. In particular, let's think about what the second part is doing. I'm taking everything in A, and then what am I putting in it?
I think that's not an A, but also.
Yeah, it's everything that's in B, but I haven't already accounted for it in A, right? So that's why these two things are the same. You need to convince yourself, draw the picture. Make sure that you really do get the same shaded region. Okay. But that's all we're doing here is instead of saying, let's take A and throw everything with B in it, let's take A and then throw everything in B that I haven't already accounted for in it. It's the same set. Okay. All right, so if I look at the probability of A union B, how can we rewrite this? What was so special about writing A union B as A union A complement intersect B? What do I know now that I didn't know before? What do I have now that I didn't have before, I should say? Mutually exclusive events, right? So what can we do? Separated by addition again, good. Okay, well, this is another thing where I mentioned before. Don't lose track of what you're trying to prove. Look at what we're trying to prove. It says probability of A union B is probability of A plus something, right? What do we have? Probability of A union B is probability of A plus something. Do you think I want to futz around with the probability of A now? No, I want that piece in there. Don't touch it. Okay? I know it's shiny and you want to play with it, but leave it alone. Okay? We don't want to touch that piece. It's the second part that we want to try to play with and rewrite. Okay? All right, well, let's think about how we can rewrite it. Now, we've already done this once. Let's scroll back up. This reminds me of, I'm going to date myself, but reminds me of high school. I had an Algebra 1 teacher who would teach on an overhead transparency that had this scroll. That's what it reminds me of. It's just, this is a little easier to scroll. I wouldn't have to crank it backwards. Okay? This part right here, we already have this, right? And those were also mutually exclusive, correct? So I know that from back up there, scroll back up, since B is equal to A intersect B union A complement intersect B, and those two sets are mutually exclusive, we have that the probability of B, and I'm going to do it all at once, is the probability of A intersect B plus the probability of A complement intersect B. It's about the 5th time today we've used that property, which is why I just wrote it down instead of going through it all again. We've written B is the union of two mutually exclusive events. So when I do the probability of B, I can split it apart. All right, going back up here, what's the piece that we want to substitute in for? Where I drew the arrow. What's the piece that we want to substitute back in for?
Probability.
We want to substitute in for that probability of A complement intersect B, right? That's the piece of the formula that doesn't match where we're trying to get to, correct? Okay, do you see that expression in the last line that we drew? Yeah, I can solve for it, right? So, all right, or probability of A complement intersect B is probability of B minus probability of A intersect B. I can solve for it, correct? And now I can just go back up to where I drew the arrow and sub it back in. So therefore, I'll just write substituting. We have that the probability of A union B is probability of A plus the probability of B minus probability of A intersect B. And then I finish the proof, so I'm out. I got a couple of Snickers. That's all I'm looking for. I'm just looking for validation for my stupid joke, so I keep saying them. This formula comes up quite a bit, so you'll want to remember it. So let's see if we can apply it. So let's look at, this is number 1.2 on the extra sheets that I gave you last time. I'll write it down if you don't have your sheets with you, but let's let E and F be events such that probability of E is a half, probability of F is a half, and probability of E complement intersect F complement is a third. And it asks you to find the probability of E complement union F, or sorry, E union F complement. There are, I would say, several ways to attack this. Let's just see if we can start playing around with some formulas. Okay. The first thing I notice is that I see it wants me to compute the probability of a union. That's what it said, right? We agree? What it tells me. It says compute the probability of a union. Okay, I have a formula for computing the probability of a union. I have a new toy. Let's play with it. Right? So we just did. So I've got the probability of E union F complement according to the formula that we just developed. How can I rewrite that? Just literally using the formula. Don't try to do any other fancy simplifying. Literally just using that new formula that we just did. How can I rewrite that? Okay, probability of E.
F naught.
Yeah, F complement, right? Yep, and then yeah, the F complement, right? I'm using E as A and F complement as B. Literally just the formula, right? Now I claim that two of those numbers we know right off the bat. One of them is really easy. We're given it, right? What's probability of E? A half, right? I already know the probability of E is 1/2. I'm not quite given the probability of F complement, but I am given the probability of F. And we know that probability of F and probability of F complement have to add up to 1. So I'm not quite given probability of F complement, but I might as well have been, right? Probability of F was a half, so probability of F complement was also a half in this case, right? Cool. I know those two pieces. So I just now, to figure out the final answer, I need to know what the probability of E intersect F complement is. Now, in my brain, there's not a lot of formula I can do with this. There is some stuff, but in my brain, there's not a lot of formula to do with this. I'd rather look at the picture and see what the picture is telling me. I can get to it using formulas and using some set theory pieces, especially looking at that probability of E complement intersect F complement. But I'd rather look at the picture. I think the picture is more instructive. Let's look at the Venn diagram. Here is E. Here is F. I don't know why I made F so much bigger than E, but it is what it is. Okay. What piece am I, in that picture, what piece am I looking for? Thinking about just the picture, what piece of the picture am I looking for? Outside of F, but inside of E. I'm looking for this picture, right? You agree with that? Okay. I need that number. Okay. What are we given with this piece? Again, on the picture, what am I given with that piece I just circled at the top? What is E complement intersect F complement in the picture? Everything outside of both circles, right? That piece, correct? Okay. If I take that second section that I just shaded, the second region I shaded, and put it together with the first region that I shaded, what does that make up? If I take the part that I shaded out here and put it together with this part that's in here, what does that make up? It's complement, right? It's the outside of F, isn't it? It's everything that's outside of F. So this shaded region is F complement, which has to be those two pieces together. So that has to be E intersect F complement union with E complement intersect F complement. Those are the two shadings, wasn't it, that we did? Those are the two shadings that we did, right? Do I know the probability of F complement? Yes. Do I know the probability of E complement intersect F complement? Yes. What else? What other special thing do I know about this set, the E intersect F complement, with regard to E complement intersect F complement? They're mutually exclusive, right? They don't have any overlap. So I can calculate the probabilities, correct? So we know that the probability of F complement is probability of E intersect F complement plus probability of E complement intersect F complement. And now we're ready, right? Because what is probability of F complement? The 1/2. The probability of E complement intersect F complement was 1/3, I believe is what they told us. So that tells us that the probability of E intersect F complement, it has to be a 1/6. Subtract the 1/3 over. So now we're ready to finish this off. So that tells us that the probability of E union F complement has to be a 1/2 plus a 1/2 minus a 1/6, which is 5/6. There are other formulaic ways to get at this. You could have, if you're familiar with De Morgan's laws, you could have rewritten E complement intersect F complement as the complement of E union F. And work with formulas that way. But a little bit more formulaic, you can do it that way. This has a picture in it anyway. So let me show you a slightly different way to think about this with pictures in setting up a system of equations. Okay? So this is actually, the second way is the way that I typically do it. I'm an algebraist by training, so if I can reduce things down to systems of equations, I'm going to do it. Okay? So let me show you what I mean. I'm going to Venn diagram it. Yes, that's a verb apparently. So I have my E and my F. There are 4 natural regions that this has now been broken into. I've got a region inside E that's outside of F, inside both E and F, inside F, outside E, outside both. Right? So I'm going to label each of those with a variable. Okay? So for lack of better letters, how about A, B, C, D? Okay? I can start setting up some systems of equations now. One that I don't even have to think about. I don't even know if I need to use it, but one that I don't even have to think about is what does A plus B plus C plus D have to equal? 1, right? Because it has to be the whole sample space, correct? No matter what problem you do, if you attack the problem in this fashion, when you add all the variables together, you have to get 1 for free. We're doing probability problems, right? So we get that equation for free regardless. Okay? But now let's think about some other equations that we get. We're given, tell me some stuff you were given. What was one fact you were given in this problem?
Probability of E is equal to
Okay, so what equation can you get from that?
B plus C equal to 1/2.
Cool, excellent. Yep, I agree. You were given the probability of E was a 1/2. B plus C has to be a 1/2. At the same, yeah, more, Megan. Go ahead. What were you going to say? You had a question? No? Did you have a question? You thought you had a question. Yes, okay, that's fine. All right, what's another equation that we must have? C plus D has to be a 1/2 because we were told what? The probability of F was a 1/2, right? Now notice, how many variables, just as a side note, how many variables are we trying to solve for in this system? How many variables do we have? 4. If I'm going to have 4 variables, how many equations am I going to need? 4, right? So I better have a 4th equation if I'm going to be able to solve this, correct? Okay? So what's equation number 4? It's going to be I think in this case it's a very simple equation. A equals a third because is it A? Oh yeah, it is A because it was E. I'm sorry, I was thinking about what we were trying to find. You're right. A is a third. Yep. Why is that? Because they tell you what?
Probability of E complement intersect F complement.
Yeah, E complement intersect F complement is a third, right? We agree? What number are we trying to find, by the way? What letter do we want out of this? Or letter or letters do we want out of this, I guess I should say. I think we want, because it wants the probability of E union F complement, is that right? Yes. So we want to do we want A plus B, don't we? Because that's A plus B plus C, E union F complement, right? So we want to find, just to write that down, we want A plus B plus C.
Why do we want C?
No, it was E union F complement, right?
Right.
So we need everything that's in E. And then, because we want everything, we want everything that's in E along with the things that are outside of F. Or we want E union F. What is it we want? I've forgotten now. E union F complement, right. So when I'm doing the union, I want everything that's in E plus everything that's outside of F remaining. So I want A plus B plus C. Well, notice I don't even have to solve this system. I'm done. I know A and I know B plus C. So I know A plus B. I don't have to solve the variable. I don't have to solve the system. I'm done. I know what A is. I know what B plus C is. I'm done. I just have to add them. And sometimes, a lot of these problems are a little bit easier to do that way. I have to figure out the individual values. Notice, I think there was more work involved in the first way we did it. Right? Literally just done in that case. Whichever way is the way that's best for you to think about it is the way you should think about it. Some people are more visual and like the pictures. Some people like the formulas and want to apply the formulas. Whichever way is fine. You'll get to the same place. We did in both cases, right?
Okay, since we're looking for like the complement of F, why are we still looking for C? Because isn't that technically an F, or because it's in E?
Because it's in E. Because union is one or the other or both. So it says it's in E but not F complement, we still want it. So the way I typically think about it is it said E, so I would have written everything that was down in E, and then, I need this to tag on the end. So if I were actually thinking about it, writing it out, if I were working the problem, I would have written B plus C plus A, because that's how my brain would work to go. I need this plus whatever's left over. That make sense? All right, so let's see if we can do another one kind of like this. Let's look at 1.5. They tell you that probability of A union B minus the probability of A intersect B is 0.3. Probability of A is 0.8. Probability of B is 0.7, and it asks you to find the probability of A union B. I've got time to do it one way. I've got time to do it with formulas or with picture. Which would you rather see? Picture? Okay. I'll leave you to work with the formula one if you want to rework it with the formula. I've got 3 minutes according to my watch. So I said I got time for one, but not both. Unless I write really fast and you don't want me to write really fast. It's sloppy enough when I'm not writing fast. All right. Same idea. I'm going to write this down with variables. Now, you can do this with 3 circles as well. It just gives you 8 regions instead of 4. So you get a little bit more equations that you might have to work with. But honestly, I took this exam when I had problems like this and was studying for this. I always drew the picture. I never worried about trying to do the formulas. Not that the formula is not important, it was just when I had problems like this, my brain worked better with trying to set up the systems of equations. I can do it the other way, but it's just not my natural instinct. All right. So tell me some equations that you can get. I have 4 variables, so at some point I probably need 4 equations, but tell me some that you know.
typically given the A plus B plus C plus D all equal 1.
Okay, good. No matter what, that's always true, right? Regardless of problem, that's always true. Okay?
The B plus D equals 0.3.
Okay, and how did you come up with that?
It's given a probability of A union B minus probability of A intersect B equals 0.3.
Okay.
So it's B plus C plus D minus C.
Right. Yeah, exactly. B plus C plus D gives you the union, right? And it says subtract off the intersection. So, like you said, B plus C plus D minus C would have to be 0.3. That's where the B plus D equals 0.3 comes from. Okay? What are the other two? Yeah, P plus C equals 0.8, and C plus D equals 0.7, and we want what? B plus C plus D? Cool. I already have B plus C, right? So really, what's the only thing we need to solve for? D. I already know B plus C is 0.8, so if we can figure out what D is, we're good, right? We agree? Okay. Well, I'm not even going to bother with the top one because we don't need it at this point, because I just need to find D. Notice this equation right here, this set of equations gives me 3 variables and 3 unknowns. So really I just need to work with those 3. I don't need the top. I'm going to use the first 2 and eliminate B, and then we'll get D. Sound like a plan? If I subtract that B, I'll call this equation 1, 2, 3 here. Okay? If I subtract equation 1 from equation 2, we get C minus D gives us 0.5. And I'm only going quicker now because I'm running out of time. We agree with that though? Yep. And then if I take that with the other one and do 3 minus this one, you'll get 2D equals 0.2. So this one was equation 2 minus equation 1. And this was, I'll call this equation 4. That is a nasty looking 4. 4. And then this is equation 4 minus equation 3. Nope. Other way around. Equation 3 minus equation 4. Sorry. I'm going to assume you can solve systems of equations. This is something you should have seen before this class. Okay. So this gives us that D is 0.1. So then I know that the probability of A union B must be 0.8 plus 0.1, so I get 0.9. Okay, easy peasy. Just to let you know, I've got solutions posted to every odd problem out of your textbook, minus maybe 1 or 2. I posted all the ones for chapter 1 already on there, so you got those for practice. If you ever need any practice problems, you can always look at odd ones. I will assign particular odd ones every once in a while for you to look at. So, in this case, I would look more at the ones that are looking like actual computing some things using the formulas. So, for example, I would look at things like 1.2-8, 1.2-9, 1.2-13. Look at those as practice. Okay. We'll get into section 3 next time, which talk about counting methods, and then I'll worry about getting an assignment out that I actually want you to turn in. Okay? All right, have a good one. We'll see you next time.